Welcome back to the Sustainable Design Lab podcast. I'm Chris Bradley.
And I'm Brodie Vander Dussen. Today we're kicking off a brand new Masterclass series focused entirely on cold chain packaging. It's one of the most complex, tightly regulated, and sustainability challenged categories in the packaging world.
And in this series, I'll be breaking down the technical side of cold chain, the systems, the science, and the decisions behind performance and sustainability.
And I'll jump in with the real-world questions that we hear every week, the challenges that teams face when trying to build systems that are sustainable, scalable, and actually function in practice.
So in this first episode, we're laying the groundwork. I'll unpack what the cold chain actually is, how thermal science behaves inside of these systems, and the market forces reshaping temperature-controlled packaging.
So let's get into it.
Let's do it. Okay, this first section is really the thermal science behind cold chain. At its simplest, cold chain packaging is a system that is engineered to keep a product within a defined temperature range from the moment it leaves the manufacturer to the moment it reaches the patient or the end consumer. Even brief temperature excursions, meaning any period of time where the product drifts outside of its allowable temperature range, can compromise product quality, product efficacy, it can violate regulatory requirements, or most importantly, it could impact patient safety. So generally, when we talk about cold chain, we're talking about 5 core temperature bands, at least in the life sciences logistics. The first is CRT, or controlled room temperature, which is from 15 to 25 degrees C. Refrigerated, which is from 2 to 8 degrees C, frozen, which is from -10 to -20 C, deep frozen, which is from -40 to -60 C, and cryogenic, which is -150 C and below. So regardless of the temperature band, every well-designed cold chain shipper includes the same fundamentals. There's insulation, refrigerants, an outer shipper, a validated pack out, and increasingly monitoring technology for real-time visibility. But here's the key idea. Cold chain isn't about stuffing insulation into a box. It's about controlling heat transfer. And there are 3 primary modes of heat transfer that we're trying to manage within the system. The first is conduction, heat moving through solid materials, and this is what R value measures. Convection, this is heat carried by air movement, both inside of the shipper and around it during transport. And then the third is radiation. This is heat transmitted from surrounding surfaces or absorbed from a solar load. So a high-performing cold chain system manages all 3 of these pathways simultaneously. Poor systems only mitigate one, which is why they will fail under real-world conditions.
And it's never just about the temperature band. It's about the lane. A 2 to 8 degrees Celsius shipment from Minnesota to Phoenix in July is totally different from a 40-mile local shipment.
Exactly. And that lane variability is the enemy of consistency. And that's why thermal modeling and validated testing absolutely matter. They take something that is unpredictable and turn it into something you can actually engineer for.
So let's get into the insulation landscape. If you spend any time in cold chain, you realize quickly there are dozens of insulation options out there. So the question becomes, how do you actually choose?
You start with thermal conductivity, how easily heat moves through a material. And R value is essentially the inverse of conductivity. The higher the R value means slower heat transfer. So let's look at the 3 most common traditional insulation materials used on the market. The first is EPS foam, or expanded polystyrene. It's reliable, it's low cost, it's widely available, but it's high carbon intensity, it's extremely bulky, and increasingly it's being banned by EPR programs like the PPWR in Europe and others. It does have good thermal conductivity. The next most common would be polyurethane. And so polyurethane actually has higher R values than EPS. So it's excellent for frozen, deep frozen, and even extended 2 to 8 C lanes. So I would, in this kind of good, better, best world, I would say polyurethane is probably better from a performance perspective. But it has some challenges at end of life. And then third, I would say, is VIPs, or vacuum insulated panels. Now, these are really cool. It's a rigid core that is sealed inside of a vacuum envelope. And the vacuum is so tight that it removes all air, and therefore conduction and convection both collapse. The R value in a VIP system can be 5 to 10x higher than what you would get with a foam. The downsides are they're fragile, they're expensive, they're carbon heavy, and they're really best suited for reuse programs. Now let's break down the sustainable insulation landscape in the same way. Let's start with starch-based foams. So this is corn, pea, or other plant-based foams that biodegrade quickly. Cruise foam is a great example. And in fact, we had John Feltz on the program not too long ago, and he walked us through how they're using it as a good cold chain solution. Now, on the advantages side, it has a very compelling sustainability story, but the challenges are moisture sensitivity. A lot of the work that you need to do is try to figure out how to keep it from dissolving while it's being used, variable density, and really the need for barrier layers. The next type of sustainable insulation you might run into are some type of natural fiber mats. So this is cotton jute, different types of plant fibers. And now these are common in meal kits and general e-commerce. You'll often see these. And it's because they're low cost and they can be perceived as more natural. But here's the challenge. They're really inconsistent in thermal performance. You have moisture absorption, and their end-of-life claims are somewhat messy. The next section I would call are these bio-based foams. So this would be things like bio-EPS, PLA, PHA foams. There's a number of different types of foams that are coming into the market. And these materials are really designed to mimic EPS performance, but with a lower carbon intensity. So the advantages are it looks exactly like EPS in many cases, with an improved sustainability profile. The challenges are it's really limited in scale. It has a mixed recycling story, higher cost than traditional EPS. And then this kind of next section is fiber and cellulose-based systems. And this is the category that has advanced the most in the last 5 years. And it's the foundation of our TempSafe platform. Again, we've evaluated all the different types of insulation materials at the lab, done extensive testing of more than 20 different materials. And we think that the cellulose has the most promise. And here's why: recyclability. So cellulose aligns with existing curbside recycling infrastructure. It's no wish cycling, no ambiguity. It's recyclable. Thermal performance. When properly engineered, and you can't just throw insulation in a box and hope for the best, you really need to make sure that the insulation is compression formed, it's layered, all the edges are sealed. Then in those scenarios, cellulose delivers lower conductivity than many people would expect. In controlled testing, it can rival or even exceed EPS for refrigerated lanes. Moisture management. Now, modern cellulose systems are designed to manage the humidity that you will typically find inside of a cold chain box without collapsing, something earlier generations struggled with. Manufacturing flexibility. So you can adjust density, thickness, and form factor, and you can tune these precisely to the lane and the payload, and that really makes this an ideal type of insulation. Now, the regulatory alignment, so EPR laws like the PPWR and state level bans are pushing really towards these fiber-first solutions. So cellulose is one of the few insulation types that is both sustainable and compliant at scale. And then I think finally, I would say end-of-life certainty. Unlike many bio-based foams or cotton systems, cellulose has a clear, consumer-friendly disposal pathway.
And I think that alignment with the EPR and PPWR is a huge deal. And so as we look at all these different insulation materials, options, the variables that it comes with it, how do we actually measure performance?
Great question. So thermal performance is a system property, not a material property. You can't evaluate insulation in isolation. Yes, you can go measure the R value of an insulation, but it won't tell you how your package is actually going to perform. The entire shipper behaves as a thermal ecosystem. And here are the key factors that you need to consider. R value. This is the conduction resistance. It measures how well the system slows conductive heat transfer. And this is a useful measure, but it's only one piece of the puzzle. Edge loss or seam leakage. This is one of the most underrated sources of thermal failure. Almost all of the design work and engineering that we do in the lab is really trying to solve for this particular problem. So even a high R value insulation loses effectiveness if heat leaks through panel seams or poorly sealed corners. So panel compliance also plays a major role. So we've talked about all of these different types of insulations. Well, if the insulation is too soft, then panels compress, creating micro gaps and heat leakage. And if it's too stiff, vibration and impact during transit can cause wall shift, and that will also break the seal. So you're really trying to engineer for a sweet spot. And that's why even we say we use cellulose insulation and temp safe, but we've developed a proprietary density that hits this sweet spot perfectly. So it's stable enough to hold shape, but flexible enough to stay sealed. And in many systems, edge loss contributes more warming than conduction itself. So these internal airflow convection pockets is another area. So air movement inside the cavity can actually accelerate warming. So we need to avoid voids, dead zones, convection loops. All of these things matter. And that's why when we're designing systems, even knowing like when you're using refrigerant and it'll thaw or melt, and if it changes shape, that can actually lead to more conduction inside the box. And so we'll even do special things with our refrigerants to solve for that. So the next thing, speaking of refrigerants, would be the PCM configuration or your refrigerant strategy. So everything really matters here. And this is a lot of the science that our lab technicians and ISTA, qualified engineers in our thermal testing laboratory will work on. And that is different PCM types, the freeze melt points, mass and latent heat capacity, and the placement relative to the payload. So a well-insulated shipper will still fail if the PCM strategy doesn't match the lane. And I should probably actually define what a PCM is, since I'm using that term. But a PCM is a phase change material. And that means a PCM maintains a target temperature by absorbing or releasing heat as it melts or freezes. And the power comes from latent heat. And there's three primary PCM families. There's water-based PCMs. So these are your traditional gel packs or water packs that you would kind of keep in your own home freezer. The freeze point is approximately 0 Celsius. They're inexpensive, they're reliable, and they're very common for CRT and refrigerated lanes. The next type of PCM are salt hydrate PCMs. And now these are engineered for ranges like 2 to 8 degrees C, 15 to 25 C, or frozen. So they have a much higher energy density, and they're very stable for long duration lanes. And then the third type would be a paraffin or hydrocarbon PCMs. These are ideal for frozen and deep frozen. It's a highly repeatable, consistent performance, and they're often paired with polyurethane or VIP systems where you really need high performance. And this is exactly why no system can be evaluated on its insulation alone. That's why we need thermal testing using ISTA 7D and 7E profiles. This is also known as kind of stress testing. So standardized hot summer and diurnal profiles, which means basically the rise and fall of temperature over a typical 24-hour period, will reveal system-level weaknesses that you can never catch from material data sheets or theoretical modeling. And that's why every system must be validated through testing. We have an extensive cold chain testing lab in our San Diego location where we can test real-world performance, through a series of chambers, et cetera. And this real-world performance really only emerges when you put the entire system, so the insulation, the PCM, the payload, the assembly method, through validated thermal profiles without testing your flying blind.
So the question really isn't which material insulates better. The real questions are, what does the system cost? What's the operational footprint? And what's the carbon impact?
Exactly. Cold chain isn't material first, it's system first. There's no universally perfect insulation, only the best system for your lane, your temperature band, and your operational constraints. And it has to be validated through testing.
So what makes the status quo not sustainable?
Good question. I think most of the cold chain systems that are in use today were built for one thing, and that's performance, not sustainability. And that shows up in a few major impact drivers. The first is there is still a very heavy dependence on EPS or extended polystyrene. EPS, it dominates the market, it's carbon intensive, it's bulky, and it's increasingly being restricted or banned, yet it remains the default in many lanes. The second are multi-material formats that block recyclability. So you take foam and you add some film and foil and plastic inserts, and now you just have this multi-material solution that really is probably going to be unrecyclable. So it's great for thermal protection, but it's terrible for recovery. And when you mix materials, recyclability drops to approximately zero. The next would be, I would say, oversized shippers and dim weight penalties. So large footprints mean that you're paying to ship air. And dim weight or dimensional weight multiplies cost across every parcel, every lane, every day.
That adds up.
It sure does. And then I would also say it's really over-engineering for worst-case scenarios. Most of the projects that we take on, we come in and look at what they're currently using, and we really help to design a better system. The system's built to survive extreme outlier lanes, even if 95% of the shipments never face those conditions. That's why you really have to do lane analysis, and you have to have different versions of the product based on those lanes. Otherwise, you wind up over-engineering, again, for this worst-case scenario, and it creates unnecessary mass, cost, and complexity.
We see this constantly. That extra safety margin feels responsible, but it quietly drives up cost, carbon, freight, storage, and labor. You protect the product, but you punish the supply chain.
Exactly. So I'd say right sizing is one of the strongest levers that we have right now. Most waste in cold chain doesn't come from materials. It actually comes from inefficient system design.
I think there's so much movement in this space. It feels like everything is changing at once. What's really driving a lot of those changes?
So right now, I would say that there are 6 major forces reshaping cold chain packaging. The first, US EPR laws. And they are penalizing heavy, non-recyclable, and multi-material formats. So states are beginning to directly price in the disposal, recovery, and material impact, and that can be significant. Mm-hmm. The second would be the European Union's PPWR. This is an even more advanced EPR scheme coming out of the EU, and it's targeting EPS, oversized packaging, and any type of empty space. So some regions in the EU are mandating take-back systems. So if you ship an EPS foam cooler or polyurethane cooler, that shipper actually has to pay and prove that they got it back from that shipment. And so you have all those reverse logistics costs. And then I would say the third are these carrier dimensional weight fees. So dim weight has become a powerful economic forcing function. If your shipper is oversized or inefficient, you will pay for it on every lane every day. Number 4, I would say, is our retailer and distributor requirements. So large retailer and healthcare distributors are now tightening their sustainability expectations based on their own sustainability goals and commitments. So foam, excessive packaging, and low recyclability designs are increasingly being disallowed. Number 5 would be consumer rejection of foam. The optics of EPS are terrible. Generally, consumers do not like EPS foam. They see it show up on their beaches in these little tiny balls. And so consumers are increasingly wanting fiber-based recyclable options, and brands are actually beginning to respond, and that's why we're seeing these types of new insulation materials take off. And then the final one I would say is Scope 3 emissions reporting. So companies now have to quantify upstream and downstream impact. And so cold chain is suddenly in the spotlight because bulky, inefficient systems carry a significant carbon load. And we do a lot of comparative LCAs. And oftentimes when we show moving from, say, an EPS foam system into a cellulose-based system, our customers are shocked because it can be thousands or even hundreds of thousands of tons of carbon reduction in a single year by making a simple change like this.
Absolutely. So it's regulation, it's freight economics, it's brand expectations, all hitting at the same time.
Exactly. And I would say sustainability is no longer optional. It's being enforced economically, legislatively, and socially all at once.
There's a lot of different factors when it comes to what makes a cold chain system good. So what does a good cold chain program actually look like?
There's 4 characteristics that I would say show up consistently in high-performing systems. The first is that the thermal performance is matched to the true use case. The system must prevent excursions. That is job one. It can't be overbuilt. It can't be underbuilt. It needs to be engineered for the actual lane, not some theoretical extreme. The second, I would say, is system-level optimization. So good cold chain design treats packaging and logistics as a single integrated system. Insulation, PCM strategy, payload geometry, conditioning, and fulfillment practice all have to align. The third is, I would say, realistic end-of-life pathways. Not technically recyclable, that isn't good enough. Not maybe compostable under ideal conditions, that's also not good enough. But real, accessible, and user-friendly recovery that works in the world we actually live in, that is what is needed. And then I would say the fourth or last would be lower total carbon footprint. So driven by better engineering, not a performance trade-off. So when the system is right-sized and efficient, carbon drops naturally through less material, lower dim weight, fewer excursions, and a lot of reduced waste.
The companies that are doing this right are improving performance and reducing costs at the same time.
Exactly. I would say good cold chain design minimizes labor, freight, material, carbon, and variability simultaneously. That's what good actually looks like. Okay, so if you take 3 ideas from this episode, let them be these, please. 1, cold chain requires a system solution. You can't optimize one component in isolation. Don't just focus on the insulation. Don't just focus on the PCMs. You really need to look at the whole system. And performance really emerges from how that whole system behaves. Number 2, is I would say every insulation material has trade-offs. There's no perfect material. There's only better or worse matches for your specific lane and use case. And third, I would say sustainability is now a performance requirement. Economics, regulation, and brand expectations have moved it from a nice to have to a non-negotiable.
A foundation matters because episode 2 of this series takes us into life sciences and GLP-1 logistics, where the stakes get even higher.
And if this episode resonated with you, follow the Sustainable Design Lab podcast and please leave us a 5-star rating.
Thanks for listening. We'll see you next time.